In this video, I wanted to revisit the up and down counter that we did in a previous video. So as you recall, in that up and down counter, I had an input X, and when X was 0, the counter acted as a mod 8 up counter. When X was 1, it acted as a mod 8 down counter. And the state transition diagram looked like this. Furthermore, when I drew the block diagram, I found that I had something like this. I had this input X into the control logic, indicating that my control logic was dependent both on the input X and on the present state. So meaning my transition from present state to next state, which is what the control logic generates, was dependent not only on the present state, but also on this input X. It was conditional on X. And now I'm going to do something slightly different. I would like to implement the up and down counter, but as a Mealy machine. So I'm going to show you how the state transition diagram is going to work for that. So it's still correct that I am going to need 3 bits to represent a mod 8 counter. And my 3 bits are going to be, as usual, they're going to look like this. Except in this case, I am going to unconditionally transition from one state to the next. So as you recall, in the previous way we had done this, I had these conditional transitions. So basically I was counting up when X was 0. So my transitions were conditional. But I was counting down when X was equal to 1. But this way, I'm just going to count up every single time. I'm just going to continue counting up. But what I'm going to do instead is I'm going to say, you know what? Depending on the state I'm in and depending on the input I have, my output is going to be different. So when X is equal to 0, I am going to output 0 like normal. And when X is equal to 1, I'm going to output 1, 1, 1, 1. Okay, let's see how this works. I'm going to do that over here also. I'm going to say when X is equal to 0, well, it's a straightforward up counter. I'm going to count from 0 to 1. But when X is equal to 1, I'm counting down. And my previous state was 1, 1, 1. So my next state is going to be 1, 1, 0. And this transition is unconditional. Okay, watch what I did. In this state, again, when X is equal to 0, so that's what this notation means. When X is equal to 0, my output is going to be 0, 1, 0. What's that? You say output. I have never talked about outputs before, so we're going to discuss those. So my output is 0, 1, 0. But when X is equal to 1, I'm counting down, and my output is going to be 1, 0, 1. So previously it was 6, and now it's 5. And again, this transition is unconditional. So here again, X equals 0, X equal to 1. So always when X is equal to 0, the output is going to be the same as the present state. And it's only when X is equal to 1 that that's not going to be the case. What happens when X is equal to 1? Well, I'm counting down. My previous state was 5. My next state is going to be 4. Here, my next state is going to be 3. Here, my next state is going to be 2. Here, it's going to be 1. And here, it's going to be 0. So let's see if this checks out. Does my logic work? Here, now let's just do a comparison. So I want to do a comparison. So this was the state transition diagram that I had previously. Okay, and in the state transition diagram that I had previously, I noticed that my transitions were conditional on X. Okay, so my transitions were conditional on X. But here I have unconditional transitions. I'm just going to transition from one state to the next, except in each state, I'm going to look at the value of my input and I'm going to output something different depending on whether I'm counting up or counting down. So looking at when X is equal to 0, I can see that I'm counting up from 0 to 1 to 2 to 3 to 4, 5, 6, 7 back to 0. So it's a straightforward mod 8 up counter. In the case where x is equal to 1, look what happens here. I'm counting down. I have a 7, 6, 5, 4, 3, 2, 1, 0, back to 7. The excitation table for this is actually just a straightforward mod 8 up counter. So hopefully by now you know how to implement a mod 8 up counter with JK flip-flops. So actually you can do the excitation table. I'm not going to show you how, but it's the excitation table for a mod 8 up counter. That's the part that's maintaining the state. The state is the outputs of the flip-flops, the Q outputs of the flip-flops at any one time. So that is going to produce something that looks like this. I'm going to have 3 flip-flops. Go through the trouble of doing the whole excitation table because there is a trick to doing a mod 8 up counter using JK flip-flops. But you can certainly, if you're not comfortable, you certainly can go through doing that as well. These are my asynchronous inputs, which depending on the logic family are sometimes known as preset and clear or set and reset, but they're usually active low. That's what this little bar means. So I want them inactive. I want this to be full asynchronous. So I'm going to set them high so they were not active. And here I'm going to just wire the clock, each of the flip-flops. Okay? And I'm going to wire J0 and K0 together. All the J's and K's are wired together. Only in the case of a mod 2 to the n counter are they wired together. So I'm counting out, basically I'm using this to count out 8 states, 8 unique states. So recall that J0 and K0 are wired to VCC, and J1 and K1 are wired to Q0. And Q1 and Q0 wired to J2, K2. Okay, but I'm not finished yet. So this is going to get me from one state to the next. This part takes care of my transitions. So if you notice, so I'm just looking at the arrows. The transitions are represented by the arrows in the state transition diagram. So I'm just looking at the transitions now. And this is taking care of getting me from one state to the next as per the state transition diagram. So it's taking me from one state to the next state unconditionally. And I have 8 unique states. That gives me a mod 8 counter. So that's good. But now I have to take care of my output. So what I'm going to do is something new, and I'm going to call it an output logic truth table. They have to derive some logic that translates from the present state into the output that I want. So if I look here, what I'm looking at here when I go to make my output logic truth table is I'm looking inside each state. I'm looking inside each state to look at my outputs. So I've sort of indicated the outputs using this kind of convention where I have the state on top and then a bar, and then under the bar, I'm displaying the outputs. And the outputs are conditional on the input. So I can see that my outputs are dependent on, first of all, what state I'm in, right? So I have different outputs depending on what state I'm in, but they're also conditional on my inputs. They're conditional, and in this case, I only have one input, which is X. It's a single binary input that indicates whether I'm counting up or down. So I'm going to show that in my output logic truth table. So I'm going to do it like this. I'm going to write out my present state, and I'm going to write my input, and then I'm going to write my output. I have not given my outputs a name, but as you can see, I have 3 bits representing the output, and because I called my input X, I'm just going to call my output Y, so not super original. So my present states are indicated by Q2, Q1, Q0, and my input is indicated by X, and I have 3 outputs, 3 bits that I'm going to call Y2, Y1, Y0. And the purpose of this truth table is to determine what they are. So as you can see, I have 2 to the 4, 16 possible permutations of Q2, Q1, Q0, and X, 4 binary variables. So I have 2 choices, they're binary. I have 2 choices for each of these variables, and I have 4 of these variables. So that gives me 2 to the 4 possible combinations. And so I filled out all possible combinations. So I have 16 possible permutations of present state and X. And what each of these means in real life, or in this example, what they correspond to is over here, I'm looking at present state 0, 0, 0, and I have 2 possibilities in present state 0, 0, 0, the possibility that X is 0 and the possibility that X is 1. So that corresponds to what's inside this circle over here, where my present state is 0, 0, 0. And I have 2 possibilities. When X is 0, my output, so remember I denoted my output by y2, y1, y0. When X is 0, y2, y1, y0 is 0, 0, 0. And when X is 1, it's going to be 1, 1, 1. So all I have to do is look at the state transition diagram and fill out my output truth table. So it's the same kind of process that I do for my excitation table, where I follow this process very methodically, where I fill out my excitation table, so my present state and next state, according to my state transition diagram. And it's the same process here. I refer only to my state transition diagram. I'm like just methodically, sort of mechanically filling in my output logic truth table based on that. So let's go ahead and fill in. So when my present state is 0 and X is 0, my output is going to be 0. Otherwise, it's going to be 1, 1, 1, 1. Now, what about the next state? You can kind of see what's going on here. So my next state is 0, 0, 1. So I'm just going to go in order here. When X is 0, I'm going to output 0, 0, 1. But when X is 1, I'm outputting 1, 1, 0. That's this here. Okay, so this corresponds to state 0, 0, 1, right? And I have 2 possibilities. X can be 0 or X can be 1. And I'm going to continue to fill it out in the same manner. So again, 0, 1, 0, I have 2 possibilities. X can be 0 or 1. That's this over here. And I look, when X is 0, I'm going to output 0, 1, 0. But when X is 1, I'm going to output 1, 0, 1. So let me go ahead and fill that out. And I'm just going to continue for all of them like this. I'm going to come to do my K-maps. My purpose here is to derive Boolean logic expressions for each of my 3 outputs, which are y2, y1, y0. So I'm going to need 3 Boolean logic expressions, which actually corresponds to 3 K-maps if you're doing it with K-maps. For my K-maps, I'm going to have 4 inputs, and I'm going to represent them like this. And I'm just going to fill it in. These 3 very symmetrical looking Boolean expressions that I simplified to their XOR equivalents. So y2 is simply q2 XOR x, y1 is x1 XOR x, and y0 is q0 XOR x. So that has a really nice symmetrical look about it. And I'm going to add it to my schematic. So let's say I have x coming in. Maybe x is the result of a switch. So I'm going to do the switch properly. Last time I didn't do the switch properly. It just kind of rushed over that part. But here, let's do a switch like this. And when the switch is closed, X is high. And I'm going to put a pull down resistor to ground over here so that when the switch is open, I am at ground. There's no current coming through this branch. So this will be my pull down resistor. And this point over here is going to be X. And then what I'm going to have is just a series of 3 XOR gates. And so here I have my full schematic. So I'm going to label the different parts of this so that we can see more clearly when we come time to draw the block diagram. So I've got my flip-flops over here with the clock input. So these are my flip-flops. And then I've got my control logic, which is super straightforward. It's a mod 8 up counter, so the control logic is actually stupid simple. And I've got my output logic over here. So let's draw the block diagram that corresponds to this. Well, this part hasn't changed. I've got my usual block diagram where I have the memory, which are just flip-flops, right? And these are sequential logic elements. So I've got a clock input. And then I have my control logic up here. And I have no X input to my control logic. How do I know that? Going back to the state transition diagram, I'm referring to the state transition diagram, and you can see that the way I've designed it here is my transitions are unconditional. They don't depend on any external factor except for the present state. The present state alone fully determines what the next state is going to be. So I have no X input going to my control logic. Where does it go? Let's find out. Stay tuned. So I've got Q2, Q1, Q0, and I've got 6 control inputs. Now there's not much combinational logic in the way of J0, K0 are just wired high, and J1 and K1 are just wired to Q0. So the control logic is pretty simple. Control logic inputs, but I have something else. I've got my output logic block now. I've got this block consisting of 3 XOR gates. If you refer back to the schematic. And this is my output. This determines my output logic along with some other element. What's the other element? So I'm going to output Y2, Y1, Y0. Now if I go back to look, so I can see this in 2 places. So let's go look in 2 places. First place, state transition diagram. I can see that my outputs, these are my outputs right here, right? And they're dependent on my present state, what my state is, but also what X is. And I could see that, first of all, I could see that in the output logic truth table. And then I translated the Boolean expressions I got from the output logic truth table into schematic form. And I came up with this. And I can see that so this is basically consists of 3 XOR gates. And here are my outputs, Y2, Y1, Y0. What are my inputs? So I have, of course, my present state, Q2, Q1, Q0, but also I have this X input, and I'm going to add it here. So it is not an input to the control logic. It is, however, an input to the output logic. And this is what makes it what we call a Mealy machine. So this is different from a Moore machine. In a Moore machine, so what distinguishes a Mealy machine from a Moore machine is simply the presence or absence of any input to the output logic block. In a Mealy machine, to be clear, in a Mealy machine, I can have conditional transitions, transitions that are conditional on some input. In other words, my transition from present state to next state depends not only on my present state, but also on some input. I can have an arrow going in here in a Mealy machine. So this is not what distinguishes it from a Moore machine. What distinguishes is the presence of this. And why do I care so much about the presence of an input to my output logic block? And the answer is because when I have that, so if my output logic depended solely on my present state, and I did not have this element here, the X input. So if my output logic depended solely on my present state, I know that my present state is regulated by the clock. It's synchronized to the clock. They change by definition, my present state, my Q outputs of my flip-flop in a fully synchronous state machine will change only at the edge of the clock. Therefore, whatever output logic I have, even though this is completely combinational, there's no clock input to my output logic. It is fully combinational, but the effect of it being dependent on my present state, which is synchronous, means that my outputs will also be synchronous. But when I add in this input, theoretically, right, going back to my schematic, I've sort of designed it. I've shown the X input as being a switch. Of course, like I said before, it could be an input from another circuit, let's say. Okay, but in this case, I've shown it as a switch. So I can open and close the switch at any time in the clock cycle, right? I'm not like obliged to do it at the clock edge. So in other words, now I have just desynchronized my output logic from the clock. So my output logic is no longer synchronous to the clock as it was before. Again, not because there are any sequential elements in here, but simply by virtue of the inputs, all the inputs being fully synchronous. But now when I add this X can be asynchronous. I can change it at any time in the clock cycle, meaning that my outputs now can change at any time in the clock cycle. So that's what makes this a Mealy machine. Why is that important? It just means that my outputs are no longer synchronous, and maybe I'm feeding these outputs to another circuit, and it's important for that circuit to know if the inputs, which are these, the outputs of this state machine, are the inputs to another circuit, and it's important for that circuit maybe that the inputs be fully synchronous. So that's why we make a distinction between Moore and Mealy machines.